Poisson distribution. Change that lambda to a mu. Now, most textbooks actually uses lambda as the parameter, but in our book we use mu, which is actually a little bit more intuitive. Right? Now, as before, when you're looking at Poisson distribution, first you need to identify the parameter, but also what is the interval. And so here, between 8 to 9 a.m., that is 1 hour. So we're saying this mu equals 4 per hour. Okay, so that is really important, the interval. All right, what's the probability of getting no calls between that time? Okay, then that's the probability of x equals 0. Okay, the parameter is 4, so it's 4 to the 0, e to the negative 4, and 0 factorial. Okay, put that in the calculator, you get 0. You get that. All right, what's the probability of getting exactly 5 calls? Probability of x equals 5. Okay, again, 4 to the 5th. You get that. Okay, 6. All right. What is the expected number? So one of the great things about Poisson distribution or modeling a random experiment using the Poisson distribution is that the expected value of the variance are very easy to calculate. Actually, you don't need to calculate at all. The expected value is 4, right? This is the expected value of x equals mu equals 4. Variance of x, right, equals, this is the symbol sigma squared, right, and also equals 4. Okay. By the way, if you want the sigma, the standard deviation, it equals 2. Okay. All right. Now let's talk about continuous probability distribution. So everything we learn about discrete probability distribution will carry over to continuous continuous probability distribution. Okay. With one exception, right, and that is this. Right. The probability. So earlier here, where we asked, we can, with discrete probability distribution, we can ask this question. We can say, what's the probability that x equals 5? Now, with continuous probability distribution, because we're dealing with continuous random variables, right? And continuous random variable, right? You can take on any value between an interval. Therefore, the probability of x equal any number, let's call it a constant, is always going to be 0. Right? We never, with a continuous random variable, we never talk about the probability of it being any particular number. So instead, we always talk about over a particular interval. Right? So now we're going to talk about the main two we'll talk about is uniform and normal. Right? And so we'll be talking about the interval here. And so what we'll always talk about is the probability of x between x1 and x2. Right? And that will be this area here. Okay, and also this area here. Right? What's the probability that we'll find x in that range? Okay. The one way to think about this is, if you have a discrete random variable, right, then let's say a six-sided dice, right? Then if you roll this dice, what's the possible outcomes? Well, you have a possible outcome that is 1, 2, 6, right? And what's the probability of each of those outcomes? Well, that's going to be 1/6 for all of them. Okay. Now, what if you have a 200-sided die? Right, 200-sided dice. Right. What's the probability? Right. What's the probability of each of those outcomes? Well, it's going to be 1/200 for each of them. Right. You have 1, 2, and all the way to 200. But then you can try to imagine, if you can, an infinite-sided die. Infinite-sided dice, right? And then, so what do you have? You have 1, 2, the outcomes of 1, 2, all the way to infinity, right? And what's the probability of each outcome? What's the probability of landing on each side? Okay, and so that's 1/infinity. Well, how do you divide by infinity? You have a infinitely large number on the bottom. This is basically 0, right? Right. And actually, we have physical objects that has infinite-sided dice, right? It's called a sphere or a ball, right? You just imagine a perfectly smooth ball. How many sides does it have? It has infinite number of sides. Right? So the probability of that ball landing on any one side is 0. The first continuous probability distribution we'll look at is the uniform distribution. It is the easiest one to understand, and it is the easiest one to use. Now, of course, not all, and in fact, most distributions or most things in the world do not follow a uniform distribution. But everything that we will learn using the uniform distribution will apply to all other distributions. Okay, so uniform. What is a uniform distribution? Uniform distribution just have a distribution shape that looks like this. Right? It is uniform. It has a flat rectangle. Okay, and this is your x value. So, for example, right, if this was income, right, then we will say is, well, the lowest income is A, the lowest possible income is A, and the highest possible income is B, and there is an equal distribution of people in low income as there are people in high income and anywhere in between. Okay, all right. So that will be a uniform distribution. Okay, now. A couple things. First of all, what is the height of this rectangle? That's going to be important because probability equals area. Right? Every time in a continuous distribution, whenever we say what's the probability, what you want to look for is the area. Okay. Now we want the area of this rectangle. Now remember, area underneath the curve or for a distribution, the area must equal 1. Okay, because if you add up the probability of every possible outcome, the probability must add up to 1. So how do I get? So what must the height be to get this rectangle to have an area equal 1? Well, that must be 1 over b minus a, right? Because what is the width here? The width here is b minus a. Right? And so remember, the area of a triangle equals base times height, right? Well, in this case, you're gonna have b minus a times 1 over b minus a, okay? And that will cancel each other out, and that will give you 1. So that must be 1 over b minus a. All right? So that is the probability density function for a uniform distribution. Okay? Calculate the expected value. That is the formula for the expected value. It's just the average of the minimum and the maximum. The variance, right, is the difference between the maximum and the minimum squared and then divided by 12. Okay. How many parameters are in this distribution? Now, whenever we say parameters in a distribution, what we're really saying is what defines the distribution. Right. In this case, we have two. We have two parameters. A is the minimum value and B is the maximum value. Okay, so let's do an example so we can understand it a little bit better. Suppose that the flight time from Chicago to New York has a uniform distribution ranging from 120 minutes to 140 minutes. So first, sketch. And we'll do a quick sketch. Okay, so what the 120 be there and 140 be here. Okay. So now, what is the height of the rectangle? That's going to be 1 over 140 minus 120, so 1 over 20. Okay, so that is your PDF, your probability density function. Okay, what it's saying here is if you're flying from Chicago to New York, the minimum amount of time is 120, that's the fastest, and the longest time will be 140. Okay, all right. So we can use this to answer this question. What's the probability that a flight will take longer than 125 minutes? Okay. So again, for each of these questions, just do a quick sketch. Again, 120, 140. Now 125 is here. And so what we're looking for is this area over here. Okay. Now once you can visualize it, you will see that, oh, well, that's just an area of a rectangle. And you know how to get areas of a rectangle. Right? It's just base times height. So the probability that x is greater than 125, right, equals, here we go, the base is going to be 140 minus 125 times the height, 1 over 20. Okay? You put that all in the calculator, you get 0.75. Right? There's a 0.75 chance that the flight will take longer than 125 minutes, or you can say 75% of the flights from Chicago to New York are longer than 125 minutes. All right. What's the probability that a flight will take exactly 125 minutes? The probability that x is equal to 125. Trick question, this is going to be 0. Right? And you can visualize it like this. Right? If you say, okay, well, I have 120 here and the 140. Okay, and here's 125. What is the density of a line? What is the area of a single line here? There's no base. The base is 0, right? So therefore you cannot, there is no value or there is no density on that line there. Okay, what is the expected value? Oh, expected value of x. And because we have a well-defined distribution, so it becomes very easy to calculate the expected value. It's just the average of the two. 140 plus 125 divided by 2. That'll give us 130. Let's get the variance. Variance of x. Right? That would be 140 minus 125. Okay, square divided by 12. So that's just the formula. Okay, and 33.33. Okay, now if I want, this is not asking. Oh, sorry. We're not asking for we don't want the variance. We want the standard deviation. So I gotta go one step further. Sigma square root of 33.33. That's gonna be 5.77. There. All right, let's do one more example. Suppose the interest rate charged for loans is between 1% and 6%, and the rates follows a uniform distribution. Okay, so right away we can sketch out the distribution for all the loans. Let's let x be interest rate. So basically, all the loans falls between 1% and 6%, right? And there's equal amount of low interest loans as they are equal amount of high interest loans. So that's how we can interpret what a uniform distribution is. All right. Now pick a random. What's the probability of finding a loan charging less than 2.5%? So here's 2.5. Okay, again, probability equals area. So the trick is just figure out what is the area you're looking for. That's the area we're looking for, and we just need to find that area, which is a rectangle. Okay? So this really just becomes more of a geometry problem than a statistics problem, right? So that's 1.5, right? 2.5 minus 1 give you 1.5, okay? Divided by 1/5, okay? Because that is the height, right? How do I get the height? 6 minus 1, that gives 1/5, okay? 0.3, okay? All right, here, go ahead and pause the video. Go ahead and give the other three a try, and again check your answer when you're done. All right, okay, so check your answer here. Again, use the sketch. All right, once you recognize the area, now it becomes a geometry problem. Right, so you get 0.14 here. Picking a random, what's probability of finding a loan at exactly 2.5%? Again, this is continuous, so any probability of